Hello, everyone. It's a pleasure to be presenting our work titled Distributed Quantization for Sparse Time Sequences. My name is Salman Salamatian, and this is joint work with Alejandro Cohen and Miriam Medar, which along with myself are at the Massachusetts Institute of Technology, and Nir Schlesinger and Jelena Avda are co-authors at the Weizmann Institute of Science. So the title of our work is Distributed Quantization for Sparse Time Sequences, and let us parse some of the keywords in this title. The first one is distributed. That many practical scenarios of interest, things like sensor networks, we get to observe distributed signals. And this distribution in space creates some complications when it comes to quantization. In particular, the encoders that get to observe each of the signals must operate independently from each other. Not only that, after the data acquisitions, there is usually a step of communication where this data is then aggregated to a central decoder to then reconstruct the signal. On the other end of the tide, time sequences. And while we're all familiar with time sequences as they arise all the time in signal processing, it turns out that these sort of sequences create some when it comes to quantization. In particular, for practical purposes, serial quantization is oftentimes necessary for time sequences. And what I mean by this is that when you get to observe a given sample at time t, not only you do not know what the future is, but your knowledge of the past is also limited, as storing an analog value is oftentimes very expensive to do in hardware. In other words, you need to do quantization in a. So a contribution can be summarized in one sentence. We propose a method to exploit sparsity to quantize distributed signals in a serial way. So the diagram of the system that we're interested in can be seen here. We'll be looking at n sources, which are each being observed by separate encoders. Each of them will generate a sequence of bits, which is denoted in this diagram by xi. These bits will then go through a network and be communicated to a centralized decoder. From the aggregate observation from the network, the centralized decoder will then generate a joint decoding of the original n sources. And this decoding, obviously, because we're looking at quantization, will be an approximation. So in other words, we're looking at the acquisition and the recovery of a set of n t-dimensional signals. So just as a reminder, n here will determine the spatial aspect, and t will be the temporal aspect. So to better explain what a system exactly is, we'll have to go through some notation. So we'll be looking at setups in which our time sequences are encoded in bit code words. These code words will be denoted by XM. Each of the code words is then conveyed to a single centralized decoder over a network. In the picture here on the right, we'll look at a simple network in which each of the encoder is directly connected to the decoder. From the network output, the decoder will operate in two steps. First, it will generate a b-bit vector, y. And then this b-bit is used to reconstruct original signals. So performance is measured as usual using the mean square error. It should be noted here that since we have n signals, we're looking at the sum of the mean square error for each of the signals. Our quantization, on the other hand, will just be the number of bits normalized by the total number of signals and the time dimension. So to perform this efficiently, we'll make an assumption on sparse, and we'll be looking, in fact, at signals that are jointly sparse. And joint sparsity simply refers to the fact that across all the nt possible entries, remember that each of our n signals has t entries. There's only k which are non-zero. This is equivalent to saying that the aggregate vector, which is obtained by appending each of these individual vectors, is K-sparse. And our goal, as mentioned before, is the acquisition and the recovery of T-dimensional signals from encoders using up to FB bits. The converse, or the other way of dual problem, is to, given a required distortion, minimize the size of the digital vector or understand the relationship with V. So our solution is based and inspired by group testing theory. For those of you that are familiar with group testing theory, we can think of it as an analog of compressed sensing, but it operates on the binary field. More precisely, our encoder here can be seen on the right. And let's walk through exactly the various steps. For each of the entries xit, the encoder will first scale a quantizer with a given resolution, here denoted by L. According to the quantized value, we'll select a code word. These code words is nothing else than a sequence of B bits. Then the code word is used to update a register. And this update is done by performing a Boolean OR pointwise. We do this for every of the time instances we have. Note that there is a special code word here, which is the all-zero code word, which is associated with the case where Si of t is equal to 0. In this case, the register is in fact not updated at all because any binary sequence plus the all-zero vector is just the binary sequence itself. There is an inherent serial structure in this scheme. And the scalar quantizer here, which is operating at step, can actually be any practical hardware-limited scalar ADC. And we'll talk a little bit more about the performance of this scheme, but we'll show that the system achieves the performance of fine resolution scalar quantization, but operates with many less bits. In the case of networks, we propose to use the exact same encoders as before, but to add a layer of coding in the network itself. In particular, at each intermediate node, we suggest to propose a logical OR operation of all incoming input vectors. Just as a reminder, the Boolean OR is nothing else. We show in our paper, as long as there exists at least one path from all encoders to the decoder, any number of network link failures in the network still leads to the same received vector of the decoder. In other words, this coding scheme actually achieves the min cut max bound in the network. There are a series of theoretical results that we can prove, and we've highlighted a few here in this presentation. The first one is so-called achievability bound, which essentially states that as long as the rate is sufficiently large, and this bound here is the bound that needs to be satisfied, then we can achieve a given average MSE. We can also look at the efficiency, which is a relationship between the number of bits that are needed here at the end of the scalar quantizer and the total number of bits here that are needed to represent our signal. It turns out that this relationship depends on the log of L on one hand, denoted here by A, and the total number NT. So besides the obvious dependence in K times A, there's only a logarithmic factor added in K. This result leads to the following corollary, which relates the quantization rate and upper bounds in terms of the various parameters of interest, namely the total size of the dimension of a problem, L, which is the resolution of the scalar quantizer, and K, the sparsity. Interestingly, we see that the rate scales logarithmically with L, but linearly with K. All right, so I've talked about codebook in the past, exactly explain how the codebook is generated. It turns out that this codebook is just a random code. More precisely, each encoder will maintain a separate codebook, which is assumed to be known as the central decoder, and will generate the codebook randomly and independently from a Bernoulli distribution with a given mean value. This specific value is just turns out to be from results in group testing. These realizations are gathered to form T times L mutually independent code words. And then the code words are then divided into T subbins. And to this, we add the all zero code word, which is the special code word. Our encoder, more precisely, does the following. Each of the incoming sample is quantized into the discrete value, Q of Sn. The encoder then uses the index that is given by this quantized value to select a code word from the E subbin. And then the encoder updates a local register. The local register is initialized to be the all zero vector. And it is updated by just being the Boolean OR operation of the current value of the register with the new value of the code word. After all of the time sequences are obtained, this is simply the value of this register is nothing else than the value that is transmitted at the end to the network. The decoder operates as follows. It uses the symbols, received bit sequences, and updates its own register. And this register will be itself operating in the same way as the register in the encoders, namely it will just perform the Boolean OR of all the incoming vectors. The recovery of the digital representation. So once you the YB, the recovery of the digital representation is based on maximum likelihood decoding. I will skip the details pertaining to this, but it turns out that there is exactly results that allow you to exactly understand the number of possible subsets with the size k, and because of the sparsity, the joint sparsity, we were able to essentially make a statement about the decoding capabilities of the decoder. All right, moving on to some numerical results. Here we compare our scheme, which is shown here in red, to the naive scalar quantization. So this would simply correspond to quantizing using a scalar quantizer of the entry of each of the times. And we also compare it to two schemes that are the references for the schemes are given here, which are based on compressed and quantized using different methods. So quantized iterative hard thresholding and fast iterative soft thresholding algorithm. This is a setup in which we have 5 distributed encoders and 20 time samples for each. And the size of our support is 3. So there's only 3 non-zero entries. Okay, the main takeaways are that we propose the serial quantization scheme with practical hardware limited serial scalar ADCs. We made use of group testing as an approach to exploit the sparsity of the signals. We showed that this architecture can approach actually order optimal compression rates. And our method integrates naturally into multi-hop networks. Thank you